Hello everyone, my name is Javier Caballeria and I'm going to present an irreversible Port-Hamiltonian model for a class of piezoelectric actuators. This work was made in collaboration with Héctor Ramírez from Universidad Técnica Federico Santa María in Chile and Jean Legorre from FEMTO-ST in France. Piezoelectric actuators are a multi-physical system frequently used in micro-nano robotic applications. This is because their small size, high resolution, high density force, among other properties. These elements exhibit hysteresis behavior, which is due to the irreversible thermodynamic phenomena. There are various control models that allows to represent the hysteresis. For instance, Prandtl-Nishinsky, Presage, Book-Wen, generalized Maxwell resistive capacitator, and hysterons. So if we consider the piezoelectric actuator as a thermodynamic system, we need to characterize the temperature of the actuator. In our work, we propose an irreversible Port-Hamiltonian system formulation of a class of piezoelectric actuators with temperature dependence, where the nonlinear hysteresis behavior is characterized using hysterons. So, what is an irreversible Port-Hamiltonian system, or IPHS? And IPHS are an extension of Port-Hamiltonian system. These are a framework that allows to represent a large class of multi-physical systems, and its main property is that encompasses the first and second laws of thermodynamics as structural properties. These laws are the conservation of energy and the irreversible entropy production. The irreversible Port-Hamiltonian systems that we can obtain can be used to design nonlinear controllers, in particularly the passive controllers, because an IPHS is a passive system. Here I will show you the definition of an irreversible Port-Hamiltonian system. It's defined by these two dynamical equations, where x is the state variable, u is the input, y is the output, G is the input mapping of the system, U represents the total energy or Hamiltonian function, S represents the entropy function. We have a matrix called JIR that is a skew-symmetric matrix and represents the interconnection of all the elements that the system has. We have a nonlinear function or nonlinear modulation function, R, that is the product between a positive semi-definite function gamma and the Poisson bracket between S and U with respect to J. This bracket also represents the thermodynamic driving force of the system. Here you can see that if we take the balance equation of the total energy function and the entropy function, the IPHS satisfies the first and second law of thermodynamics. Here in this first block, we have the conservation of the energy. And in the second, we have that sigma S represents the internal entropy production of the system. Before I show you our proposed model, I'm going to talk about the hysteresis representation using hysterons. The hysteron consists in the interconnection of two basic elements, the energy storage element and the resistive element. Here in figure 1, you can see a hysteron for a mechanical system. The energy storage element is represented by a nonlinear or linear spring, and the resistive element is represented by the nonlinear damper. We're going to use hysterons because this is a passive approach to characterize the hysteresis curve of the piezoelectric actuator. The interconnection of several hysterons allows to construct more accurate and complex hysteresis curves. For our proposed model, we're going to consider that one histogram is the interconnection between a nonlinear resistant and a linear inductor in series. The resistance is nonlinear and have this constitutive law here, where Wj is a nonlinear, smooth and nonlinear operator that depends of the current of the histogram and the temperature of the piezoelectric actuator, and satisfies this dissipative relation, where sigma Hg is the internal entropy production of the J histogram. Well, now I'm going to introduce to our proposed model, but first I have to talk about the model developed by Goldfarb and Seranovic here at figure number 2. They model the piezoelectric as an electrical mechanical system, where the mechanical subsystem is represented by a mass spring damper interconnected by this transducer element. The electrical part, we have a voltage input source, a capacitor, and this block here, MRC. This block MRC is the generalized Maxwell resistive capacitor and is the element that allows to represent the hysteresis behavior of the piezoelectric. So our proposed model, we're going to take the model from Goldfarb and we're going to make some changes. The first one is that we are going to characterize the hysteresis behavior by using histograms here. We are not going to use the MRC. So we have the nonlinear resistance interconnected with the linear inductor. And the other modification is that we're going to assume that the coupling element, the transducer element, G, is temperature modulated. Here down, you can see the constitutive laws, where alpha is the electrical mechanical transducer ratio, which is a function of the temperature. Then from the previous model, we obtained the following set of state equations. And note that the temperature is a function of the entropy, and we're going to model it as an exponential function of it. Finally, we have the irreversible Port-Hamiltonian formulation for the proposed model. Here in equation number 1, we have the dynamical equation. Number 2, 3, and 4 are the definition of the interconnection matrix J0, JD, and JJ. And number 5, we have the definition of the nonlinear modulation functions. The input vector is composed by an external force, voltage source, and the external temperature. We have here the definition of the input mapping G, and finally our conjugated output Y. We perform some numerical simulations to the proposed model, and for this consider that the external force is equal to 0. We use some standard physical values to the parameters of the electromechanical components. Here you can see how we define the electromechanical transducer ratio. For simplicity, we use only 2 histograms, both equals. This means same value of inductance and same nonlinear operator. And we define the nonlinear operator as you can see in figure number 4. So here we have the results of the numerical simulations. At figure number 5, we have the hysteresis behavior between voltage and displacement. We use a sinusoidal source of 100 Hertz and 100 of amplitude. And if we increase the external temperature, the slope of the hysteresis changes. At figure number 6, we have the static temperature change for different frequency operation. Now we are going to vary the frequency of the sinusoidal, and we're going to use different values of inductances for the histograms. And we expected that as long as the frequency increase, the temperature increase, but this is only achieved in ranges of values of frequency. And this changes as long as we choose different values of the inductor. At figure number 7, we have the step response for different environment temperatures, and we can see that if we increase the external temperature, we can see a bigger offset in this step response. And finally, at figure number 8, we are going to see the hysteresis curve for different frequency operations. And if we increase the frequency, the hysteresis curve gets wider and its slope gets decreases. In conclusion, an irreversible Port-Hamiltonian formulation for a class of piezoelectric actuator with temperature dependence has been proposed. The electromechanical dynamic of the actuator has been modeled using a nonlinear resistive capacitive inductor circuit coupled with a mass spring damper system, while the nonlinear hysteresis has been characterized using histograms. Numerical simulations have shown that the proposed model is capable of reproducing the expected behaviors of the piezoelectric actuator. And finally, in future work, we'll deal with the control design and experimental validation. Thank you very much for listening.